and the principal of the college to please come.
Om Shri Gurubhyo Namaha Harihi Om Sahana Bhavatu Sahano Bhunaktu Sahaviryam Karavavahai Tejasvinavadhetamastu ma Vidvishavahai. Om Shanti Shanti Shanti. Harihi Om. Bhadram karnebhih shrunuyama devaah Bhadram pasyamakshbhiryajatraah Sthirairangaistushtvagum sastanubhihi Vyashema devahitam yadayuhu Swasti na indro vridhashravah Swasti na pusha vishvavedah Swasti nastarksho arishtanemihi Swasti no brihaspatirdadhatu. Om Shanti Shanti Shanti. Harihi Om. Purnamadah Purnamidam Purnat Purnamudachyate Purnasya Purnamadaya Purnamevavashishyate. Om Shanti Shanti Shanti. Harihi Om Tat Sat. Shri Ramakrishna Arpanamastu.
Next, I would like to invite our Principal Maharaj to come and say a few words.
Om Namo Bhagavate Ramakrishnaya. Respected esteemed members of the Calcutta Logic Circle, we are extremely happy to host the second edition, at least as far as the Narendrapur College is concerned. So this is the second time we are hosting this. And as in the previous edition, I do hope and pray that this becomes a grand success. Of course, I didn't participate in the earlier event, but then based on the feedback that we received from the participants, I definitely come to this conclusion. One humble suggestion that only I can put before you, that towards the end of the two-day Congress, can we have a public lecture specially meant for the science stream students of this college, or even philosophy? If that is possible, that will be a big blessing to all of us. So that is my humble suggestion before you. So with this, once again I thank one and all, Pulokda and others who are insiders, as well as esteemed members of the Calcutta Logic Circle. Om Shanti Shanti Shanti. Harihi Om.
Next, I would like to invite Joyantada Professor Joyanto Shen to please come and say a few words about the Calcutta Logic Circle.
On behalf of Calcutta Logic Circle, we welcome all of you, those who are offline, and some of our friends are in online also. According to, it's a informal body, but we have a rule that who will attend a seminar is a member of Calcutta Logic Circle. So all of us, some of us are already attended past seminars. So most of you are members, but who are new in this seminar are also members of Calcutta Logic Circle. Now I say a history of Calcutta Logic Circle, a few words about history. Having in mind a sincere desire to learn fundamental issues of logic, a study group was formed in 1987 in Calcutta with the initiative of Professor Mihir Chakraborty, Professor Amita Chatterjee, and late Professor Ranjan Mukhopadhyay, all of whom are founder members of this group. This study group, which was informally named as Calcutta Logic Circle, CLC, received constant inspiration from the late Professor Horogauri Narayan Gupta. He was a PhD student of Professor Tarski. Professor Pranab Kumar Sen and Professor Tushar Kumar Sarkar, Philosophy Department of Jadavpur University, also supported this initiative actively. From the beginning, this group comprised members from various disciplines like mathematics, computer science, philosophy, and provided appropriate ambience for interdisciplinary exchange of opinions and views. Though initially it was a study group, it gradually developed into a research group. Some of areas in which research work was done and is being pursued by members are rough set theory, fuzzy logic, paraconsistent logic, set theory, vagueness, approximate reasoning, modal logic, belief change, linear logic, logic of diagrams, etc. We used to organize weekly seminars, but for past 2 or 3 years we cannot do it. But we regularly, at least annually, we organize a seminar for 2 or 3 days. In the present year, it is 2 days. Apart from weekly and annual conferences, very special events and workshops are also celebrated by Calcutta Logic Circle on World Logic Day. Very recently, in memory of Professor Newton da Costa, in August 2024, a workshop of paraconsistent reasoning is also organized by Calcutta Logic Circle, and some other seminars. So once again, on behalf of Calcutta Logic Circle, we welcome, and we hope that all of us will be enriched by this 2-day conference. Thank you.
Should I share your slide? So the first speaker of a technical talk this morning would be JAM, Professor R. Ramanujam, and he's going to talk about reasoning with a question mark underlying large language models. Welcome, JAM.
How do I move this? Okay, I can see that, yeah. No. No, I want to move back now. How do I move back? I can use this. This is simpler. Good morning, everyone, and it's a great pleasure for me to be at Calcutta Logic Circle always. I'm I think okay. Oh, yes. It's okay, we can. Huh? We carry on? Okay. Yeah, so I put in the title as reasoning with a question mark, underlying large language models. That, when I suggested the title, I said reasoning underlying large language models. Put a question mark at the end and then realize that there may be a confusion with that. Certainly something is happening in large language models. Would you like to call it reasoning is the main idea. So, yeah, so thanks to Shaurav and Calcutta Logic Circle for the invitation. It's always a pleasure for me to, it's homecoming for me. I think, it was said that it was started in '87. I heard about it in April '95 and I came in August '95 for my first time, and I think I've come many, many times since then. So it's been a great journey, I would say, and learning and also affection and friendship, really. So thank you very much for continuing this very important thing. I've been part of the Tamil Nadu Science Forum for a long time, been doing voluntary work and various things in science communication. I know what the spirit of voluntarism means. And I think in logic, if there is voluntarism, it's entirely represented by Calcutta Logic Circle for me, because it's really entirely voluntary, a group. And for academic activity, that is very rare. So I think it's a special thing to mention here. Well, so this talk is on large language models, ChatGPT, all this kind of stuff. So caveat, let me first mention that I'm not an expert on LLMs and approach this topic only due to the apprehension that logicians cannot really afford to ignore this kind of developments going on in artificial intelligence and generative AI, as it is called. So there is a recent flood of papers on this topic, and I'm surveying a small fraction of that. Not really presenting any original work. I'll mention a little bit of things here and there. So, how many people have seen ChatGPT, used it, seen it? Okay, enough people. So, they're very impressive, right? Because even with a lot of use of artificial intelligence, nobody thought that you can write essays, write poetry, right? In fact, it's very interesting because to ChatGPT you can give an essay by somebody and say rewrite it in the style of, say, Conrad, and it shows something fairly impressive. I mean, this is really impressive. That, right? I give a paper in the style of Mihirda and say rewrite it in Kamal's language. I don't know if it can do it, but at least literature I have seen, and it's fairly impressive. So the point is, it's a language model, and whenever there is a language model which is impressive, a good question is, surely speaking, right? Whenever we use language in a sophisticated manner, we would assume that there is reasoning going on inside, right? Is it possible to exhibit sophisticated, so that's why I'm saying, sophisticated language behavior, not just communication. Now, I remember Rohit Parikh and I were long ago working on it, and we wrote a paper on semantics of messages and so on. There is always this thing that maybe you can make sense of communications, messages, without underlying grammar. I think it's possible. But if you're talking about sophisticated language behavior, like essays, poetry, whatever, is it really possible to do it without a sound underlying logical base? Now, I would have always thought that logic is at the bottom of this, right? I mean, I remember in one CLC, in fact, my talk was on logic and cognition, and which is more fundamental, Is logic underlying cognition or cognition underlying logic? It's a pity that this is a line of research that we have not progressed much on, but I think it's a very important question. Same thing here for me. Looking at GPT, the first question was, is logic underlying a language model or is the language model underlying logic? Either way, there should be something going on. There's been a lot of discussion on whether generative AI is really understanding, right? And people have been writing articles saying, yes, it is general AI, yes, it is understanding, and no, it is not, etc. But my point is something else. Maybe it is not understanding in the sense that you and I, but it's doing something. What is that, right? Can we, so there is some reasoning going on. What is that? Maybe it is not the logic that you and I use. Maybe it's a different logic. What is that? So this is where it starts from. The main point is, how do I then look for logic? You're having conversations with language models. It's typically question answering. Do the answers reflect some coherent internal belief system, which we can call rational? And then what are the rationality postulates that we can derive? I mean, this is very far from answering any of these questions, I must say. So can they be said to be reasoning at all? Now, some researchers are skeptical, some researchers are super enthusiastic about the whole thing. I don't know. So there is this paper, it's quite already very influential one, where they say that we qualify that although chain of thought emulates the thought processes of human reasoners, this does not answer whether the neural network is actually reasoning, and the emphasis is mine. Now, what is that? If you can do chain of thought that is very similar to human reasoning, processes of human reasoners. So you're saying that it reflects something like the thought processes of human reasoners, but it's not reasoning. What is that? How do we distinguish these things, right? I think AI is making us ask good questions. Let me put it that way. I'm not sure. I don't, but finally, I don't especially care about what GPT does now. But my point is that it forces us to ask certain fundamental questions about logic that we talk about. And certainly philosophical logic, which you take very seriously. So this is the point. Even if we term it informal deductive reasoning, can we extract some formal logic from the patterns of question answering, right? So in general, if I go to suppose I go to some Mars, right? Somewhere, go to some civilization. And I can see, all you do is to do some question answering. Can we just observe the question answering process and deduce some logic that must be there? This is the point, right? If that is so, surely large language models, we should be able to extract some reasoning. Now, what would you say about readings of this? Yeah, so, no, there it's different because ELIZA especially, right? These programs started with logic, right? See, this is the difference between logic-based AI as we have known for 40, 50 years and neural net deep learning-based AI, right? This, we'll see a bit of the, encoder architecture and all that, right? So this is a very different way of how AI has built up. And these two branches are almost completely separate, right? And it's extremely impressive technology, what deep learning has shown today, right? Deep learning plus now transformer architecture has given us this large language models. This is very different from logic-based AI development, right? Now you're doing hybrid models and so on. We'll see. But my point is that if I just look at neural network-based stuff, yeah? So ELIZA is different. I wouldn't. So the answer, there it's much easier to see what is the logic because you build logic into it, right? And expert systems, rule-based systems, they were all logic-based approaches. Yeah.
See, this word, this phrase, large language models,
Yeah.
I came to know only very recently.
Yeah.
Because I was asked to review a paper on large language models. I thought it is something literal, large, then language, then
Yes.
models. All the three words I knew. So perhaps I'll be able to say something about make out something about the paper. But when I accepted, I saw that it was completely different. It is a purely technical term and something else. So my interest will be if you say,
I will
at
take
least
a little bit
define
about
a
the-
little bit of what.
No, I will
language
definitely
model
talk a
is.
little bit about the techniques underneath. But it will be necessarily very, very condensed thing, but I will say something about it. Yeah. So there is a lot of stuff going on. Like I said, there is a flood of papers, and I am choosing to talk about 3, and these are all, look at the dates, huh? July 23 and October 23. Okay, this is by these guys' standards, I think in neural network, this is all already old stuff, right? 2024, there are so many papers. So I am deliberately choosing to say, okay, at least I will not look at 24, right? So there are 3 approaches which I found reasonable, which I can summarize, and that's what I will do and use these. And there is one fourth, which is not so much with this, that's more a logic-based approach, but I want to see, connect it up as I go along. And by the way, that Adnan Darwish's paper is based on his invited talk that he gave in ICLA 2021. And that's what he has been developing, and that's what his. So it's also, an ICLA paper that we should pay attention to. Yeah, so first let's just look at this. You have software like GPT, right? Just forget LLM, ChatGPT, right? Now, before we get into whether it is doing reasoning or not, supposing I want it to do reasoning in a particular way, right? Rather than, I don't want it to be question answer, but I want it to actually do some reasoning. How do we do it? So there are several approaches based on that. That paper by Y and so on is really what is called chain of thought prompting. You keep asking questions in such a way that from the questioning, and you are controlling the questioning, right? That's the idea. You keep asking questions in such a way that you can build a chain of thought. It's a very nice way of going about it. For instance, you say, typical school arithmetic sort of thing. Roger has 5 tennis balls. He buys 2 cans of tennis balls. Each can has 3 tennis balls. How many tennis balls does he have now? And the chain of thought, you can extract actually a sequence like this. It says Roger started with 5 balls, 2 cans of 3 tennis balls, each is 6 tennis balls, and 5 plus 6 equals 11. And finally, it says the answer is 11. I, in fact, looked at this paper mainly because I'm doing a lot of work in math education with children and so on. And we usually try to see how children reason in classroom with small children. And this is precisely how you do. And that's really the chain of thought experiment you can do with ChatGPT. And you can see actually. So I must say that with these models, you can actually see it reason in this sense and actually come up with answers, explain the answers in this particular way. So the model actually learns to generate explicit rationale before producing the final answer. You can actually teach it to say, don't give me the answer, tell me the very steps, right? Which is what we tell children. In the exam, you're not supposed to write the answer, you're supposed to write the steps, and it's the steps that carry the marks, right? Something like that you can do. And this is basically, in one slide way of talking about chain of thought prompting. There's a lot of technical work, I'm not going into that, but you can think about how this happens. Now, as I said, there are already many papers studying reasoning in these, but most of them, they're really telling you, they define some reasoning task and they show how well the thing does, performance. They don't actually get into a rationale, right? And how would what is the rationale behind whatever reasoning it's claiming to do, that you're claiming it does. So chain of thought prompts, if you do, you can see that the individual steps are valid. The point is, you can see that even if I give it an ontology that is completely fictional or completely counterfactual, right? So it need not be with tennis balls and this, that. Huh? This is also very interesting. We don't have time, otherwise I would tell you about experiments of that kind that you can do. Create a completely fictional universe with different laws, and you can see it follow certain chain of thought. But often you see that if there are multiple choices, it makes wrong choices, and therefore the proofs are wrong. Again, I was looking at it principally because this is exactly what children do. right? And that's alarming to me. I would much rather that GPT follows a very different reasoning than children do. But this is also, I mean, first, I must say that it started off with the linear algebra problem I was giving. And I tried with the linear algebra problem, and then I found that it was making mistakes exactly like a typical undergraduate students do, right? You give a set, you forget to check that it's linearly independent or not, you are calling it a basis without even bothering to check, exactly the kind of problem. And what was very interesting to me was I prompted and say, hey, are you sure these are linearly independent? He says, oh yeah, this is not this thing, therefore it's not a basis. This was very deeply worrying to me. I would much rather that GPT do crazy mistakes. I don't want it to be making the same sort of mistakes my students in my class are doing, right? But so I wanted to see what was happening. So that's how this business started. I don't think I have much clarity on that. I'm sharing some ideas with you, that's all. Yeah, I don't know. So, yeah. So, it's very interesting. There is this paper where they show that they give it a fairly complex reasoning task. And it's able to, planning task, and it struggles with it. I mean, right, it tries something and something goes wrong, but it's pretty decent, I must say. But then on the other hand, there are some absurdly simple planning tasks it's not able to do at all. So this is also a very strange combination. But my point is that there are many papers in the last 2-3 years, that's all I looked at, but few actually make clear whether they are reasoning or simply using memorized patterns and some heuristics to solve problems. And I don't know, this is a mess, okay? And of course, AI, this is typical. There is a lot happening, lots of activity, lots of papers, but getting clarity is very hard. And there is no real ontology even to clarify it, I would say. So one particular thing that I have taken up, and this is this case, Kastner et al. And Delia Kastner is a kind of influential figure in the deep learning community, so I thought. So what they do is to do iterative querying. So it's not one-shot question answer, but you keep repeating, trying in various forms, and you do. And they construct a kind of a belief graph, and use that belief graph to evaluate whether the answers are rational, right? Because if you want to say that, is there an underlying rationality, coherent belief system, I should build a belief graph. This is their way of approaching that. For instance, you want to know if I heat ice, what are the things that happen? These are the multiple possibilities that are given to the program. It changes its chemical makeup, will leave a puddle, it makes it even colder. These are the options given, and it's supposed to choose whichever is the best option. This is not choose the one that's true or false sort of thing, right? And so they test the model on some 20 related assertions. There are lots of assertions, all very close. Heat cannot cause a solid to melt. Melting means leaving behind a puddle. Melting results in a puddle, and so on. And remember, this is a language inference. This is a language model. It's not any other. So the assertions form the node of the belief graph, and they infer edges between the beliefs, how one belief leads to another, based on the responses. And what is very interesting to me is that they actually, because of that, they're able to show inconsistencies in its belief system, so to speak, and thus hope to get the model of, and they are interested not to see whether it does reasoning or not, they want to teach it to do reasoning, so to do correct reasoning. That is their goal, a typical AI system goal. So, and the belief graph is something like this. So you have, every node has a triple, there is a statement, and a level, as they call it, but basically a truth value, and some confidence in that truth value, right? So this particular statement is it true or not, with some confidence level in the real interval 0, 1. And then there are rule nodes. These are the belief nodes, and then the statement nodes and rule nodes, which are typically clauses. It says if S1 to S2 to S1 and S2 and S3 are true, then either T1 or T2 or T3 are true. So this is how you represent the belief of the, and again, some confidence in this particular rule. And so the cost of a node, now you can associate, is 0 for setting it to L, and whatever is the confidence level for setting it against that. And they take an exponential this thing. Because these people are deep learning, Boltzmann, see, it started off with Boltzmann machines at Jeffrey Hinton. They got the Nobel Prize, no, this year because of that. So typically they use e to the minus some cost function. That is, I don't even know if you ask why are you doing that, not very clear explanation, but it's just that their deep learning community is used to using Boltzmann distributions, so they come up with some version of this functions like this, and overall weight is you take this thing, sum it over the incident edges, that's what you will get it. A typical way neural network community works. And so you take the exponential of the sum. And now you can, you get some distributions and you can look for the most probable explanation that minimizes cost. Network will do that and you can adjust parameters and you can do. This is typically how they do. So even as they use LLMs, large language models, as a black box for reasoning, what is very interesting is they are trying to explore dependencies. And what is interesting for me is that they don't just say that there is an inconsistency, but try to explain it and try to repair it, right? So to do that, they take the belief graphs into an equivalent weighted maxsat problem and use a maxsat solver, so they can actually see how, So maximum satisfiability problem is that how, what assignment of truth values, what is the maximum assignment that I can make to this thing that makes the clauses true. And they make no claims about internal reasoning and so on. They are not doing any such thing. They're probably not interested also. Their main thing is that if they can add what they call a rationality layer, some rational belief system on top, then it leads to correct reasoning, right? It won't make mistakes. So they're not really interested in seeing whether LLMs are rational, but they're more interested in, can I make it rational somehow? So what is very interesting for me is that they do a good mistake analysis. Again, as an educator, this is for teachers, this is always a more interesting thing. Why do my students make the mistakes that they make, right? So they find 5 main causes of failure and actually give frequency distributions of these things and so on. That's also quite sophisticated. One is missing rules roughly account for 1/3 of the mistakes. Incorrect beliefs are only about 1/3. So it's not really. Incorrect rules are only about 10%. So it is not that the system is coming up with rules that are actually wrong, logically speaking, right? Ambiguous statements, only about. So this is a language model. So that is one of the good things, right? It can deal with ambiguity without much difficulty. And multiple correct answers, only about 10% of the time. So, okay. So this is one style of work where what you are doing is create a situation which involves reasoning, and then you see how the system performs by doing experiments on it. And out of the experiments, you construct some way of talking about whether the system is doing things in a rational manner and try to explain it using standard probabilistic arguments. Okay, now this is when Mirza wanted and yeah. So you need to do a little bit, you have to look at a little bit of detail about the internals of large language models. I'll try to give as global definition of it as possible and over just some 10-15 minutes. But obviously, anything where you do it in 15 minutes, it's going to be very, very crude, so pardon me for it. People here may know many internal details. They can add to it. Maybe I don't know well enough, but I'll try to give this thing. So this is this unique hard attention transformers, as they are called. It's a class of transformer encoders. I'll mention this. See, what do large language models do, right? They are basically predictors. If I give a sequence of words, if I give you a text, it's supposed to say what is the next element in the sequence, right? I give you a sequence and ask what is the next element in the sequence. Except that now what we are asking is text. Since that's why it's a language model. If I give you a text and ask what is the next phrase that will appear, right? So large language model tries to suggest that this is the next phrase with a very high probability. That's all it does. How does it do that? Natural language. Most of these things are done for English. As far as I know, the two really large language models are for English and Chinese, right? And so when you say model, usually you talk about how big is the parameter space. This thing is of the order of 1 trillion. I mean, GPT-3 was some less than 1 trillion, but GPT-4, GPT-5 are all of the order of 1 trillion. Beijing Academy of Artificial Intelligence, their LLM, they claim is 1.3 trillion. So these guys talk, I mean, so when you say large, you mean large. Okay, so, and abstractly what is going on, how do they find out what is this thing? So you can think of it as every word is, it's got lots of attributes, right? Syntactic, grammatical, semantic attributes. So think of it as a point in an n-dimensional vector space. This is the main idea. Like you can describe Kamal in terms of his height, amount of hair he has, and his, the specs he wears, whatever, right? So a whole bunch of attributes, right? Suppose you choose 10 attributes, you will put Kamal as a point in a 10-dimensional vector space, right? And why vector space? So that you can do some computations. Think of it that way. And all those elements are real valued. Integer, real valued is good enough, right? So the vector space you can think of as Rn, right? But the point that we are now talking about is that every word is an element of a vector space, but the dimension of the vector space is, when you say n, we say n, 10. No, don't think of 10, don't think of 10,000, think of 10 million. That's the first point, right? It's a vector space, it's a humongous vector space, and you have notions of metrics so that you can navigate along these things. So when you talk about the text that you already have, you have some representation. So you've already built up some trajectory in this vector space, and when you're talking about the next element, you are talking about using some metrics in that vector space. It's all probabilistic to find something next. This is broadly what's going on in this. So the transformer architecture, what it does is to take that, does an encoder. So these things are called transformer encoders. They'll actually map it into elements of vector spaces, do the manipulation, and the decoder actually maps it back to words and these things. That's how these things work. And that transformation that is going on actually are affine linear transformations. So not big deal, huh? Easy to understand. They're affine linear transformations, so it's not. But the thing is, it's over a number of layers. So this is what they call multi-layer deep learning, right? Deep learning means many, many layers of applying these things. Very clever, fancy stuff is, nice mathematics is done to do this part. Not at all difficult to understand. If you'll spend some few days understanding it, you will find it. As I said, this is a class of, so this is what was happening, and this is why, Hopfield and Hinton have got the Nobel Prize, got the Turing Award a few years ago. Dramatic technology works very nicely, right? And, but it was very difficult to implement, and for language models, sizes were becoming humongous. Few years ago, from Google DeepMind, there was this group of researchers. They wrote a thing called "Attention is all that you need." Now it has become the most cited paper, I think, in all of, So what it does, what it says is that you don't just look at, use those metrics. You come up with this idea of, something like homomorphisms on vector spaces, right? You bring it down to something. So that's the attention idea. There is something called hard attention and soft attention. It's a little too much to go into, but basically some way of reducing it so that you can focus, and in the process of doing that, you can bring in semantic attributes. So that's been the revolution of this transformer architecture. Vector spaces, yeah. So in principle, these are not vector spaces, these are lattices. So I'm glossing over. So they're not vector spaces, they are lattices, they are integer coefficients, vectors with integer coefficients. Yeah, it's all with E minus. So I don't know. I am not, I'm telling you what it is, that's all, right? I'm just saying that this is how the the network, neural network, deep learning community has built up and what they are doing. Yeah.
Why all this is being at all studied?
Uh-huh. Yeah, it's a good question, yeah. Okay, so the other line of work that I want to mention is to look at the internals of that and deal with it abstractly in a logical sense. And there is this very, very interesting paper by Hahn and co, where they show that if you actually set up the right mathematical model and study it, you can show that they accept, you can look at them as language acceptors, and they are contained in AC0, which is basically the class of Boolean circuits of unbounded Fanon that have constant depth and polynomial size. It's also one way of thinking about this class is that it's an extension of first order logic with all numerical predicates, where the calculations that you are doing are all indices on sequences. It's first order theory of linear order. On words you can think about it, but you are doing arithmetic on those indices. So this is basically the kind of logic that. So I thought, okay, maybe you can look for logic in a very formal sense, right? Look at simply this as mathematically something is happening. I don't care about the significance. It's a class of structures. So what is the first order theory, right? Seems like a reasonable question to ask. And here there is a theorem that I'll mention. So okay, these guys say it's contained in AC0. What about the converse? So this is this paper from last year that shows that not all AC0s can actually be accepted by this. So there are actually polytime languages not acceptable by these encoders. And they in fact show that they recognize all languages recognizable in the first order, the monadic extension of first order logic. It's monadic here, it's called mon, but what they mean is really unary numerical predicates. So this implies basically for me the interest was that every formula of linear time temporal logic using only numerical predicates has an equivalent representation as a transformer encoder. So okay. So for me, I can understand that proof is horrible, but I can actually understand it in terms of linear time temporal logic, and it makes sense. And it's not that surprising. As I said, language model, what does it do? Once again, what is it? Given a sequence, it tells you what is the next in the sequence. So it's a kind of linear temporal reasoning is not that hard to think about. But to pin it down formally and prove the theorem is a lot of work. And I'm not going to take you through that, but I'll give you some idea. See, what is this going on, right? Forget that, there's some mistake there. So it's well known that first order definable languages are a subclass of regular languages, and extending first order with even a single unary numerical predicate such as evenness is not definable in first order languages with order as well, but you can add something like x is even to get all regular languages. And what are unary numerical predicates? Basically infinite families of functions. For every n you have theta n. So which says that given a word, we'll always be looking at non-empty words. Empty word creates technical difficulty. So when you say a word, I mean only non-empty word over some alphabet sigma of length n. You say that the predicate theta x holds at I if and only if the ith value, right? If I take the ith index, that makes theta n true. Theta n of I is 1. It's a numerical predicate over numbers from 0 to n. So it tells you whether this number satisfies this property or not. It's some numerical property, arithmetical property. That, okay, this is 0 to n minus 1. Remember there are n plus 1 indices. Nth thing is actually reserved for certain summary information. Some clever coding is needed. So for instance, now I can write a predicate like middle, right? I can write n is even and say that I is the middle element. And once I do that, I can define context-free languages, because why I can say, once I find the middle element, I can say, hey, all elements less than or equal to that middle element have an A. And then after that, I get only B's, right? If x satisfies this, PA of x, and if x is y satisfies that, and y is greater than the middle element, pb of x. That tells me, that will give me the language a to the n, b to the n, which is a context-free language. So my point is that this numerical extension of first order can help you define context-free languages, but not all context-free languages. I don't know. That's actually a nice. I was just telling Kamal that I think a characterization would be nice. You know it's contained in AC0, but exactly where it is. Two-thirds, one-third, two-third you can. So that's why I said it has non-empty intersection with context-free languages, context-sensitive languages, and I can see linear time computable all the way. So that's why I'm saying it's a non-trivial extension. A good precise characterization is also interesting. I mean, this has nothing to do with LLMs, any of these things, simply a mathematical question of, logical question of interest. So, I've already put it, 2n by 3 is also there. So 2n by 3 is also interesting because it's in AC0, but it's not in this, right? So you can, so it's quite subtle. Something is going on which, requires some work. And this is, again, last year's paper. This thing is, there is a lot to be done. Maybe that will have nothing to do with GPT, but it's worth doing. Yeah. So what is this transformer encoders with attention that they call it? So pick some dimension, but remember when I'm saying dimension D, I mean maybe 1 million or something like that. Finite dimensional vector space, we are used to thinking of 5-dimensional, 4-dimensional, 10-dimensional. These guys have no problem. So an encoder layer abstractly are only these things. There are the 3 affine linear transformations. So always we are doing this RD to RD. We are only talking about linear transformations RD to RD. And the C is going to take thing of from dimension 2D. Okay. So there are 3 transformations. And for any j, you take a vector uj and you set it to vjk, where it's the maximum element that maximizes the so-called attention score. What is this attention score? Apply pointwise both the A and B transformation and take the dot product, right? That will give you the attention score, and you're looking for the argument that maximizes the score. This is basically what one layer does for you. And then you take that. So once you have computed Vi, now you've got this other vector Vi, and you set it to some Vi prime, which is applied by the third one, right? It takes 2 of those vectors. You got one that focused the attention, you got that output, and that you take with the whatever input vector, that is, you will get a 2-dimensional thing, 2D dimensional thing, apply C, and what you get is the output. This is how it, so this is typically what one layer would do, but what they call standard layers can do arbitrary position-wise affine transformations. You assume that pretty much any affine linear transformation that you can come up on this space Rn, I can implement using the network. So you freely mix what you want out there. And then on top of the standard layer is something called ReLU. Let's not worry about it. I'm again telling you just what you need for the proofs. So basically it's a function. It takes any vector and applies it to a particular coordinate. So if I've got V1 for the Vi is actually this V1i to Vdi, then what it will do is to take all of these and at the kth place, right, it applies, it checks whether Vik or 0, whichever is bigger. If it is less than 0, all negative values, it will make it to 0, and it does here. So this is what is called ReLU layer. So what it does, the reason why they do it, what it is not important for me. The reason why they do it is that all you need is a constant number of them to implement any position-wise function. You can implement position-wise any function which is a composition of affine linear transformations and max. So this is a very, very nice theorem. This requires proof. There is a lot of work that goes on, but it's not very, it's just linear algebra. I assure you, you can sit and learn this very carefully. So what is this UHAT that they are building? It's simply the repeated application of standard encoder layers and ReLU encoder layers. That's all. Of course, when they say a number of layers, see, the dimension is in millions. The number of layers is in thousands. So, but mathematically, it's all finite dimensional. Everything works very nicely and simply. The simplicity is astonishing for me. Now, so I can take these models. These models are not weird for us to do logic with. What is the problem? I mean, model theory, we are used to dealing with whatever kind of vector spaces. Is that any problem? Not at all, right? Now, to code it up, these things as languages, and so that I can think of it as acceptors, some extra masala is needed. So you have one function which takes takes vectors as alphabet symbols, and there is something which has become big in the machine learning crowd, which they call one-hot encodings. I don't want to get into all that. But so you need one function, another function that provides positions of the symbols on the input word. And remember, what is going on, these sequences, finally we are doing in a language model. The sequences are text, right? So where a particular word appears, the position carries a lot of significance. That's really the point about positional encoding, right? So the function will tell you, which particular thing. That's where you need arithmetic on indices also. And then you have a vector that finally tells you whether it should be accepted or not, based on several attributes. So it's a vector because of different attributes. So how do you actually talk about it as an acceptor? You say a language is accepted by this model. If I can find this, see, remember there are these three functions, f, p, and a vector. So f is basically you take the alphabet, it maps it into this d-dimensional vector space. P is 1, which given any pair of numbers, it will tell me one vector. And and this final vector t, such that on a word, the representation of t hat of t is actually greater than or equal to 0, exactly when for the word belongs to that language, and it will be less than 0 for all things not in the language. So this is a standard way you can talk about acceptors. And how do you define this t hat of w? So basically, your output is t and some vector v0, where I give it the sequence, input stream a0 to an minus 1. Then it's a transformer, right? The transformer will take a0 to an minus 1 and produces n vectors v0 to vn minus 1. When given, what do I do? On the input stream, I apply f first, and then positionally, the second vector p, I apply from 0 to n, and then f a1. So this will be the first output. Second output will be f of a1 plus p1 to an, and so on. Right? Positionally, I keep shifting and I am applying all of them, and I'll get the output vector. So positional encoding is very critical here. Without this, the problem is your encoder can treat input sequences in a permutation invariant way, and you don't want that. You want it to be less. So you can ensure that. And the main idea is that you remember that attention, I told you, was a big revolution, right? That attention is all that you need. If you actually work out logically what is going on in the model, so that attention is actually being used to guide search along the sequence. And so now I just want affine transformation. So negation, I simply implement as 1 minus x, or I implement as max of 2x minus 1, 2y minus 1 plus 1 by 2. That suffices. That will give you negation and disjunction. Then remember, I'm going to explain it in terms of temporal logic. So then you need a successor function, right? I need negation, disjunction, successor, and until. But once you get successor is the really difficult part, and that's natural. All temporal logics, defining the successor function is the hardest work on first order theory of linear order in general. So you need to design, so for the successor function, you design one of those U-hat layers where attention is always maximized on at the next position. That's what it shows. I'll take that up separately. And for the rest, basically what do you have to do? Given my sequence 0 to n minus 1, and any minimal index for each of these satisfying a given formula, I'll create one U-hat layer where for every position I, the attention is actually maximized at ji. Attention is just a function. You're looking at what values it takes, and you're looking at the maximum value of that function. What gives you the... So the details are tricky. But remember that semantically, if you were to think of in the language model what is going on, when you say in this sequence, remember the sequence is humongous, but we We are calling, for us it's n, right? But the n value is in maybe in billions, it doesn't matter. But what you are saying is that I am looking for that word, right? Attention is telling me which are the places I should be looking within that for predicting the next one. That's semantically what is going on in that. But mathematically, this is all that it's doing. Details are tricky and depend on designing suitable affine linear transformations. That is mainly work. I'll just show you for the successor function and skip the rest. So the hard work is in the implementation of the successor function. So what you do is you take your, it's going to output a sequence of vectors and linear transformation such that argument wise, right, it takes the maximum, which is actually the unique one. The next one is the one that maximizes attention. How do you come up with that? It turns out that the vi I need is cos pi 1. Remember, the 2 to the minus I is the main function that they use from the Boltzmann distribution, right? So you do cos of pi 1 minus I by 10. This is complicated calculations that they do, right? This is like typical in all mathematics, right? You have to reverse engineer and see what values work for you and do. But this is, of course, an affine transformation. That's all you need, right? And then you need one curious linear transformation that reverses the third coordinate, some horrible technical detail, but it works. It all works nicely. And given that, I can define that linear transformation AVIVJ. Cross product of that, if you calculate, you get this one nice number. I think I have maybe, there is one extra parenthesis there, otherwise it's okay. And then you can show that for any fixed I, this is exactly the quantity that is maximized for the successor. So all this work suggests that, so I mean, do internals matter? Is always the question, no? Does the hardware matter for the reasoning, right? And we would like to believe that the brain structure that is evolved actually matters for reasoning, right? Hardware matters. So this is I think it's a good philosophical question as far as I'm concerned. So what is clear is that in principle, LLMs are doing some first order reasoning. Not in the way that these people are doing experiments and showing. I'm saying, after all, if I look at it as you are telling me given a text, however long, given a text you are predicting the next thing, you are doing some temporal reasoning. You are doing some first order reasoning. And I can try to precisely pin down exactly what, I mean, this is something that we have, come on. I have learned for the last 30 years, spent my life doing various kinds of first order sequential reasoning here. I mean, so we should be able to do that. So this kind of theorems we can prove, right? So that may actually give some idea of abstractly saying this is all, first order reasoning of a particular kind, right? So in principle, I think you can give explanation. Now, on the one hand, this is guaranteed. If we prove this, it's a theorem, okay? That's exactly. And this is much better than the kind of hopeful, wishful black box testing that I was telling you from the AI papers that I was seeing, right? Trying to see how it does. Unfortunately for me, the problem is, I mean, this one is an abstract one, right? I am not claiming that this is what GPT is. I have no hope of understanding GPT. Remember, OpenAI is now property of Microsoft. They're not even going to tell you the design. In fact, it's not even clear to me whether those guys know the design that well either. I am giving, so be very careful. When we are giving this nice linear algebra picture that comes from the mathematical study of the deep learning networks and transformer architecture, which they claim they have implemented in GPT. That's all. Software engineers work in a different world, right? I don't know whether there's actually, supposing I prove we get, Kamal and I, we have worked a lot on all this kind of thing. FO with some particular numerical predicates we can precisely define. Maybe we can define those encoders. We all know enough linear algebra to do this business and tell this thing. Surely, neural network people should be able to build these things. Why? But I don't know. Why would they do that? Like Mirza said, why do you want to do that? It's a different story to me. Yeah. So we do not know this is very important. We don't know the actual details of the internals of GPT-3, Turbo, now Bard has come, Google has come up with its own. Remember, there are only 5 or 6 companies in the world that do these things because there is tremendous computational power, huge billions of dollars is involved. It's not something that, Ambani has to think twice too before he can set up something like that. Certainly not you and me, okay? So we don't know the actual details of all these things. So one way is to go back and do, okay, can I do logic but in a slightly, maybe do that kind of experimental stuff, but from that do logic in a formal way. So one thing is that after all, neural networks were built to do classification, classifiers, right? Image processing, this is all they were meant for. Maybe we can infer logic from the classifiers that they have got. So what is a classifier? It's essentially a function that maps instances, take the entire input space and map it into a finite number of classes. It's an equivalence relation of finite index. So each classifier has a set of features which are discrete or numeric variables, and an instance is generated by assigning a value to a feature. This is how image processing, for instance, is done. I'll not do too much of these things. So can we use large language model as a classifier and infer whether the reason behind the classification is rational? So for instance, suppose there is a pregnancy test based on 3 features: urine test, blood test, and a scan. In this case, the classifier has 2 classes, right? Test is positive or negative. So given an instance which represents the test results of the patient, classifier first computes the distribution on the variable p that gives these results. And a classifier could have been learned from data and a decision made by some probabilistic reasoning. But as far as we are concerned, it's actually a map from the variable space to the 2 elements at 0, 1. And these variables are discrete, and because they are discrete, I can code them up as Boolean formulas. So, and here I'm referring to the work of Darvish and his students. So again, linear classifiers you can compile into a decision graph. Not go into details of this. Yeah, in the variables, in the example that I said, all variables are discrete, and we can do binary. So the point is that if somebody gives you a decision graph based on all these parameters, right, wedges, it says, okay, decide on this or decide on that with some probability, right? Now, it corresponds to some propositional formula. I can assume that formula to be in negation normal form, and then a binary classifier is giving me a pair of formulas, beta 0 and beta 1. Now, when an instance I is classified as one of those, I give it an instance, and this network is telling me it's beta 0 or beta 1. I want to know why. How do we find out why? That is the question. So we want a condition on the input I that actually implies beta I, right, where I is 0 or 1. So that will tell me the reason why in this instance I classify it as beta 0. What conditions? How do I find that? Well, Darvish has a very interesting definition. So the complete reason for the decision on instance I is the weakest negation formula. It's something like an interpolant. Think of it as a formula gamma, such that I implies gamma and gamma implies beta I, but I'm looking for the weakest gamma. That's what you want to find out. So that he calls the complete reason because it's the weakest one that is implied. So you can think of it as the weakest interpolant of I and beta I. Now, then you can see that it's monotone, and you can use these properties of that. So how do I then say, okay, which are the ones that are justifications, right? You take a literal x, it's an implicant of beta if x implies beta, that is natural. It's a prime implicant if no other implicant actually is weaker than it. And what is very interesting is that actually prime implicants are very good, because by setting these two literals to true or false, I can actually arrive at this decision. So you can think of these as adequate reasons. And so this I find as a very compelling way of doing things. They play of course in complexity theory you know that they play a very important role in the theory of Boolean functions. And there are these things like minimal covering sum. There is this Blake canonical form. This is all much used in the study of circuits and complexity of circuits today. So again, I can do some standard kind of reasoning. So it gives some kind of minimal set of characteristics that justifies the decision in that instance. And let me skip on this thing. So they are, abductive explanations, you can compute it in linear time. So, and the point is that Boolean variables are not important. All discrete variables you can handle this way. Continuous variables are different. But so in some work that I was doing with a couple of PhD students at Tsinghua, we were looking at some of these. So we thought, okay, we can take, at least I give decision problems to LLMs, GPT. And then vary the input variables systematically and see how it arrives at decisions. And from that, maybe we can infer some logic. So we can, point is that it's a simple to write an algorithm that constructs a decision graph. And from that graph, very easy to build a tool that will give a Boolean formula from which you compute the prime implicants and then use them as the sufficient thing. So I'm saying it's little better than the kind of black box testing, right? They're based on some logical principles that you're. So we offered some, we found some problem in decision theory. It's like theft insurance of bike, okay? So you want to buy a bike and you want to take insurance, and the specification is what is the value of the bike, annual premium, and where you park it, what's the probability of typically where you use, probability of it being stolen, and question is whether it's worth insuring the bike or not, right? The premium costs are quite high. So we were looking at this is from a standard decision theory textbook. We said, okay, we'll take only textbook problems from decision theory and see what it does. And initially we tried with 6 values and already we got 143 prime implicants. 3 values we got only 12 and we could do this. So the main point is that as the probability of the theft approached 0, systems seem to consider this as certainty. This is again something very typical in probability theory courses students do, right? If it tends to 0, it is 0. I mean, now this is a real problem, right? A small, extreme events can be dangerous. But this is something that routinely GPT was also doing. And then it ignores all other information and simply says bike need not be insured, right? So, but the probability was more than 20% or so, then it would do expected utility calculations and then it would do correctly. So boundary cases are a problem. Normal cases, it can do a reasonable job. This is the kind of inference we could see. Now, I don't want to sell any of this. So point is that my suggestion is only that maybe there are professional logical ways of looking at these things, right? Rather than typically what I see in AI today, which is, GPT experiments, right? But there's probably, I think it seems worthwhile to consider algorithmic means for checking some rationality of reasoning in LLMs. At least for Bayesian classifiers, I think we can algorithmically determine what I put within quotes, reason behind decisions. And this seems better than black box testing. And it's too premature to say whether these things will give you a rationality model or not. And the deep question for me is whether language behavior can generate logical reasoning, right? In itself is really the deep question. Okay, thank you. Yeah.
Okay, so we have time for some quick questions.
My question is, there is a lot of other group, like Professors Subbarao from Arizona State, looking at ChatGPT versus planning, classical planning problems. So are they of the same category, or reasoning and planning you tend to separate out?
Yeah, so the Valmiki paper that I referred to, there are 2 papers that appeared within a few months of each other. One which was showing how this is generative AI which can do pretty much any of the classical planning problems. And then 2 months later, another paper appeared saying what it's doing is not planning at all, and showing dramatic failures in very, very simple planning problems, right? So this is, and then now you see, that's why I said, as I mentioned, something very bizarre is going on. GPT, at least GPT-3 and was the turbo GPT-3 and GPT-4, right? These were those experiments. Complex planning problems, it was actually showing very interesting results. Not optimal, but interesting results. Very simple planning problems, it was screwing up badly. So this is not like the kind of rationality model that we are used to. That's all we can say right now, right? But BARD, Google is putting up BARD, which seems to be better at these things. No, nothing about this. The truth is, from what I see, at least the handful of papers that I see, very difficult to come to any reasonable conclusion either way to me. That's all I can say. But yeah, a lot of people are studying, trying to use it for planning and so on. But the quality of the plans it generates is questionable.
Okay, so we are running a little behind schedule. So one quick comment or question. That's all we can. Yes.
Yeah, it's first of all, thank you for the nice talk. It's not really a comment, more of a question. Like the first part, in the first part of your talk, you mentioned this transformer architecture. You tried to explain what it is all about, the encoders, decoders, kind of the stuff. Whereas in the second part, you moved on to ultimately like the classification problem and how to analyze those. So ultimately, when you are doing that, you are trying, kind of seeing it as a black box in some sense.
No, the second thing is only black box. It
Yeah.
has to be because we don't know what GPT is. See, these are all proprietary software, right? Building that thing from corpus and this took them 2 years, 3 years. They're never going to even repeat it, right? I mean, that's how all this language models are built. They go over a corpus. They use internet, all your WhatsApp messages, all that. It's all data for them, right? So they're sitting on humongous amounts of data, and trawling that, they build a model. That's what they have done. That's exactly how these are built. And they're not going to tell you the details of that. So you can only use these as black box. The other part is, if you could look into the black box, this is what you would see. And this is what you would see mathematically. But when you talk mathematically, you could be doing wishful thinking. Right? We know that very well, right? What a in general, what programs are supposed to compute a function. So if I tell you that this program computes this particular function, you can go and write the program yourself, but in the belief that you are doing what this program is doing. That is that middle part. The other part is there is no way we can, it's easy for me to say all these things, but I can't build any of that. You and I can't build. So we have to rely on this software. So you can only do black box. This is where we are.
Yeah, but you were saying that it's all affine transformations.
Yeah.
But meaning affine transformations, there are some weights, and it's all about how you're assigning those weights, isn't it? Whatever
not,
that
no,
is.
this is very,
it's
it's
also
not
a
how
very important,
you assign
meaning
weights.
how the weights are being assigned. It's not. Of
They're
course, it's
automatic,
not
no?
Me.
Yeah.
Yeah, but that's the crucial point there, because.
Very crucial. But the critical thing is that, remember, the data it's data sensitive, right? It is the data that it's what do you call it? That it's given, from which the weights are computed. But how else do you and I learn, right? As human beings, as children, right? Babies, right? Small children, babies, they observe. They're like continuously data is pouring in. Based on that, some network is formed in the brain. This is what they're trying to model, and that's what they're trying to implement, right? So the weights are continuously adjusted, right? GPT, you can do many experiments, right? One of my colleagues in math science, I think Manjari, right? She was reporting on this. Every day at a certain time, she would ask the same question. It's just the bloody thing is learning, right? Over 1 week, I can see the quality of answers has changed because, so it's continuously learning. So weights are not assigned. See, it's easy to make
Definitely. But it's also kind of trying to understand. If you want to try to understand the transformer architecture itself, it's also about understanding how these weights are assigned.
How these weights are computed.
Meaning from one layer to another, from one layer to another.
Yeah, so we can talk about how they are computed, and you can see that. But the picture, mathematically, we tend to do is a static picture, remember that, right? It's a static picture. It's just, when you say sequence of transformations, you could apply that, compose it, apply it as one transformation. Now, what is that? There is no problem. Mathematically, it makes no difference. But in reality, what is going on is something dynamic. So there is that, gap between the mathematical model and the actual thing that's
That
going
I
on.
completely agree. Yeah.
So there is a lot happening there. So these abstract pictures are meant for us to understand. How else do you and I understand? We can't hope to understand anything else, so we do put it this way. Let me put it that way. I am not an engineer, right? But the main problem is that neither are those engineers understanding what is going on. They build these things, they have no clue how it does, right? They build this humongous structures, right? Their only justification is it works. They're able to, you can download it on your mobile, right? You can download it on your mobile and you can actually give it something and it gives answers. That is the justification for them. They don't care. It's a company. Remember, this is not produced from a university. 6 companies are doing this whole thing. That's all.
This weight thing, is it related to review somehow?
Yeah, of course. Of course it is. They are ReLU.
That's why review is important.
That's why ReLU is involved. And not one, every layer has one. So there are thousands of them sitting there. How do you even know how to compose any of them?
Self-improvement being done continuously.
It is. It is doing continuously, and as I said, you can see that it's learning, right? It's visible. It's visible learning. And somebody has done this experiment. They actually put it something like 100 terminals. So simultaneously, you can see what's going on. Everybody is interacting, doing the same thing, right? For instance, these kind of problems, you can say students working at terminals, right? Within 1 hour, it has learnt across because all it needs is data. And this is what has changed, right? See, none of this could have been done in the 90s, 2000s. Of course, technology is available. Another important reason, there is no social media, right? Now humanity, you're voluntarily all continuously providing data to WhatsApp, right? So for a language model, there is no greater delight. Continuously, we are all supplying data voluntarily to 3.5. WhatsApp is a company, let's not forget, right? So you're providing data. So Meta and Alphabet and all have data sharing agreements. All these data is continuously coming and it's continuously learning. So then they realize that you build this humongous model, invest a few $1 billion into it, 1 trillion model. As I said, Beijing Academy has produced even bigger one now. So in Chinese, they've got huge amounts of data. Remember, China has always had its own separate thing, right? So they've got all that data. That's it.
Okay, so in the interest of time, we will have to
Thank
cut
you.
this here. Please let's thank the speaker again. Okay, so I owe you a few words about the confusion that ensued before the talk. So there are 2 programs. One is the main conference program where Jam was to be the first speaker, and there was also the inaugural program where he was supposed to be a speaker introducing or saying a few words about CLC. So I saw the time. The conference was supposed to start at 11, so I assumed that this is going to be the technical talk. So I missed one of our speakers in the inaugural session. So let's please welcome Professor Parthasarathi Mukhopadhyay to say a few words on behalf of the college and the department.
A very good afternoon, everybody. I don't know how far logical it will be to extend a warm welcome to you after the session has already started, but then still allow me to do that. Calcutta Logic Circle, it's a very vibrant body, as we all know, meets regularly. And though I used to consider myself not really a part of the body, my junior friend today has put forward kind of axiom, only befitting a logician, that whoever is attending the seminar must automatically be a member of the Logic Circle. So that's how I became a member. And then really I'm got into mind that being a member myself, whether extending welcome will be a self-referential problem. So anyway, just like every circle has to have a center, and for me, the Logic Circle, the center happens to be my beloved and respected teacher, Professor M.K. Chakraborty. With his beautiful teaching, we are all fascinated right from our university days. And sitting at the center, he always exerts a kind of, what should I say, a centripetal force dragging us in to roam around in this circle. So thank you, sir, once again, and thanks everybody, all other dignitaries coming from different places, and people who are participating online. I extend warm welcome to all of you on behalf of myself, my college, and my department, and hope this grand success. Thank you very much.
Thank you, Parthoda, and sorry for the confusion. So we can have some tea now. 10 minutes break, tea and disappointed হবেন কেন? Okay, so we will have to start our post-tea session, otherwise we are going to run further behind schedule. You won't want to miss the lunch here. Okay, so there is a slight change in the schedule, so let me first announce that. At 12:45 there was a talk scheduled by Professor Romita Chatterjee. Unfortunately, she's not well today, so that's why there is a change. Instead of her, talk will be given by Professor Amit Kuber. Anyway, so with that, let's start the post-tea session. Our next speaker is Professor Shamanta Hajarika, and he's going to talk on affordance, abduction, and explainable AI. Over to you.
A very good afternoon to all of you. It's a pleasure to be here. Thank you for the invite, Calcutta Logic Circle. So I'm going to talk about affordance, abduction, and explainable AI. After Professor Ramanujan, it's difficult to talk about explainable AI. I will try to give you an idea of what I meant by these three terms. But what is more interesting for me is sharing three experiments that I have conducted in my lab in order to take forward this idea. Now, for people who are not very aware and curious about what I do, I design intelligent assistive devices. I work in the area of prosthetic hands and hand exoskeletons, design controllers for them. But these controllers, when I design, I exploit machine learning and artificial intelligence. And that's how I am related to logic and look at logic more closely. So I'm going to talk of these three things and show you some experiments we have done in our lab working on these systems. For cognitive scientists or people interested in cognition, affordance is a term that they may be already aware of. Abduction is something I even am scared to talk to a group of logicians. You know abductive reasoning better than me. I will try what I mean by abduction. And explainable AI is what part of Professor Ramanujan was trying to emphasize. So let me begin with explainable AI. What do I mean? Can we go beyond the black box? So the discovery and formulation of explanations about what is going on in complex AI systems is something not new, but is newfound enthusiasm there. People want to understand what is going on inside these complex AI systems. And trying to understand this is what is covered roughly in explainable AI. And the need for explainable AI has risen because of the very fact that we perceive current machine learning as opaque. What is going on inside is not known to us. And we want to come out of these black box models. So I'll show you a curve here in terms of interpretability and in terms of model accuracy. These black boxes, as we call them, these complex CNNs, deep learning models, are very high in terms of accuracy. But in terms of interpreting the results, interpretability of these systems in pure mathematical logical terms, even to write them, is a very complex procedure. Okay? So we are very high when we are talking of rule-based learning. We know what is happening inside. We can interpret the results correctly. But as we move away, even for classifiers like support vector machines, and moving on to deep learning, accuracy increases, but interpretability is lost somewhere. And this is where is the main focus of research. Can we understand or interpret the results coming to us? So that interpretation happens in two ways. There is post hoc explainability techniques. That is, you interpret the results and try to understand why did this result come from. Okay? So in terms of features, in terms of the procedures or inference rules that you had, where did it come from? And there are hybrid modeling approaches where you, in the system itself, want to put new explainability preserving approaches so that you have features that you could use for interpreting. That's called interpretable feature engineering. In the features itself, you keep features so that they comes up and you know that this is the result because of that feature. All said and done, one should understand that most of machine learning is actually induction. It's neither deduction nor other forms of logic. It is induction. So even if we are doing interpretation, modern explainable AI remains far away from telling us or providing human-like answers. And that's why Professor Ramanujan's talk was very interesting to me, saying ChatGPT does it the way children do. It's exciting because to look at this, why? Most of explainable AI remain far from providing the human-like why. Instead, results only boil down to causal attributions. So that is a problem, okay? So what can be done about this? We have looked at a way of reasoning, the abductive reasoning, that is what differentiates the type of reasoning from deduction. Okay. Okay. You want to stop me? So I continue from here? No, it's okay. I continue from here? Yeah. So we are looking at abductive reasoning, which is different from deduction and induction, and which involves inferring not from some deterministic axioms or inferring general statements, which is about explaining observations. So most of you are aware of abductive reasoning, but what makes our abductive reasoning so important and interesting is that abductive reasoning is actually an exploratory activity. Because abductive reasoning is exploratory, and because explanation search in these AI systems is also exploratory, it is felt that they fit hand in glove. So we are having for this the idea that one expects to interpret the outputs and seek to find explanations. So this idea fits in hand in glove, and we have this challenge of implementing abductive reasoning and automating the explanation process very well. So that is the motivation. In order to explain AI systems, particularly my intelligent assistive devices, in terms of what is going inside, we fall back on a concept called affordance. So we are looking at affordance. For many who knows affordance, affordance is about relationship between the user and the object. So like if I see a chair, I know it affords me to sit on it. If I am looking at a jar, I know it holds water. So if I look at a glass, I know I can drink water from it. So it's about capabilities of the agent vis-a-vis the properties of the object, and that allows me to do stuff. So with affordance, what is happening is, I can look at the reasoning cycle of an agent, particularly in activities of daily living, and use these affordances as anchors for the point where abduction starts. So these affordances serve as natural anchors for me to understand how did he go about to do the reason. Like let's say I give an example. I have a glass here or a cup here, and I want my robot to lift it up. So when my robot is reasoning where to lift it out, how to lift it up, the anchor for his reasoning starts with affordance of that object. So the cup gives me an affordability of grasping in the handle. So this is the reason which my AI reasoning system should pinpoint to me, saying, yes, this is the region where you should hold it. So this is the reasoning happening, but that reasoning, affordance serves as a natural anchor. So this is a thesis here, that any form of reasoning that is happening in daily living activities for an artificial intelligent agent affordances are the natural anchors. So with that, we put together this system of affordance-driven abduction for explainable AI. Any artificial intelligent AI system that I am developing for my intelligent and assistive device, if I can explain it, I want to explain it in terms of abduction and affordances. So I need to observe first, detect what are the affordances in the environment. Then I use the affordances to infer possible actions or intentions. And then I do the decision explanation in terms of the affordances vis-a-vis the reasoning that I have done vis-a-vis the final work. So in order to do this, I conducted 3 experiments. The first experiment that I am going to report is about taking mental imagery as a starting point, looking at electroencephalogram data. So I capture real EEG data of 50 students coming to me, looking at things, and I want to find out, is affordance playing a role here when they reason out? Okay, so let me show you that experiment, the first one. So I ask my subjects to imagine things. That's called motor imagery. So I asked them to imagine about nailing in some wooden ply. So you show it a hammer. The moment I show a hammer, I should know that he must be thinking of hammering. Okay? So that's the affordance of the hammer, and he must be thinking of hammering. Affordances of hammering. Sorry, kya ho gaya? Piche chala gaya. I show it affordances of hammering. That's motor imagery. I ask him to do motor imagery. Together with motor imagery, I ask the subject to also observe, or what is called action observation. So I run the subject to do only imagery. I then ask the subject to do only action observation, and I ask the subject to do both the things together. So this is what is my protocol. I do pure action observation, pure motor imagery, combine action observation and motor imagery, and look at what is called ERPs, or evoked response potentials. So I take measurements of EEG data from these locations. Now people uninitiated to EEG mapping, we have a cap, we have 10 electrodes this side, 10 electrodes this side. That's called the 10-20 system. Okay, so I take these electrodes. Out of this, the only middle patch, C3, C4, CZ, is what my motor cortex is made up of. My motor functions are dependent on that, so I look at that, the motor cortex. Okay, so when I look at the motor cortex, I look at 2 things. One called the N1 potential, which tells me that you are able to visually look at things. Your visual attention is very good. And I look at another called the N2, which is the existence of affordances in your visual screen. So my thesis was that if I was looking at an object that was having some affordance, and I was thinking as well, I should have the maximum N2. Otherwise, in other cases, I would have minimum N2. So I looked at this topographic plot of the amplitudes of N2 component. And to begin with, when you were observing, you had very high amplitudes. Okay, so that's it. But when you have combined, your higher amplitude was retained. See, it passed off after some time. Here, it was retained. So what does this, and not only satisfied with this, yes. Milliseconds. Oh, these are milliseconds from the start of your experiment. So the moment you are given the input, so you are told that here is a screen to the experiment. So if you see this curve, your experiment starts at 0, whereas your experiments start at 0, whereas N2 becomes only at 110 and beyond, and N2 is 200 plus and beyond. So this is the time. I'm after stimulus. It's not only eye tracking. So we track the eye to see if attention is there. People without attention, not including the analysis, but attention with time. Stimulus, attention with time. No, only visual. Our stimulus is only visual. Only visual. Occipital node, there was a probe. We have put it. We put all our 32 channel probes. I am trying to only highlight for my C3, C4, CZ right now. We have all the probes of my 10, 20, 32 channel probes. Okay. So I'm just highlighting only because I'm not talking to a group of cognitive scientists. I thought I'll just highlight what I wanted to. Sorry about that, being rough there. But I just highlight the motor cortex, and I'm trying to prove my point that once I have this, and then I convert my EEG data to what is called low resolution electrotomography analysis about how firing is happening in your brain. So I look at this when only AO is there, and when only MI is there, and when combined AO-MI is there. So firing is huge here. So what does this conclude to is the following conclusion. When I am imagining with affordance, and if affordance is added as a cue as well, okay, so it enhances your motor function. That in the literature says anything enhances, that means that affordance cues, okay, there is a natural link between affordance and reasoning that I am doing for my ADL. What is this trying to say? Let me repeat it again. I ask you to imagine, I give you cues. If I give you cues, you are doing it better. So why you are doing it better? You are doing it better possibly because you are using affordance for your reasoning. And that's why affordance cues are helping you to reason or imagine things. With that in hand, we go and look at our second experiment. We ask a person to use a microwave, keep on doing this, and this person at least knows that the microwave is lightweight, the microwave is having a non-detachable door, the box is near to the microwave. So we want our AI system now to really get the semantic affordances from the system itself. Okay, can my AI system get semantic affordances from the video itself? So we try to learn the semantic object affordances. We give the video inputs. We have an ontology of objects. So we have an ontology module, object property extraction is happening in that ontology. We do a lot of primitive entity generation, and then we learn which are the semantic affordances in that particular scene. Having got the semantic affordances, we use it in our deduction module, a knowledge-driven layered reinforcement learning, which I am avoiding. Some learning paradigm I'm for recognizing intents from the video. Based on whatever affordances I have learned, I'm trying to use those affordances in my reasoning module to really understand what is the person doing in the video. Why? Even before the person is doing. So let me put it that way. So I am understanding intent rather than the video action. Why intent? Then my assistive device is going to go and help it there. So that is what I do. I get all these semantic object affordances like has concavity, non-detachable part, medium weight, and this looks like as if this is a first order type of very, very restrictive language. So we use it that way, and we have all the semantic object affordances identified. Finally, having done this, having found that affordances play a role in reasoning, Second, that semantic affordances can be automatically found out. I then want to explain, like this person is passing on a plate to this person. So I want to now really want to understand and explain all of these in terms of my affordance and abduction. So I create a theory of the space, the domain, the objects. This is spatial and temporal, only qualitative. And I have here numbers. So what I do is I have a qualitative abduction theory, and I have an underlying numerical number going on, typical vision stuff. I build a bridge between them. So I have a framework of high-level formulations for logical abduction, low-level visual processing. I create a integration between them, and from that integration, I then find out the most optimized, consistent hypothesis that can explain the video here. So this is the visual explanation. This is the third experiment that we have done. Okay, and this experiment requires that my theory part is all space and time, but qualitative. So I create something called temporal graphs, which is nothing new. We create temporal activity graphs, which are spatial relations between different components. And then we create what are called temporal edges between different times because of the different frames. And we create this temporal activity graphs. And we do our reasoning in terms of a very simple visual abduction theory. If we find the set of logically consistent hypotheses, high-level events and beliefs grounded in very low-level motion tracks. So the abduction is very simple. It has some spatiotemporal ontology, a spatiotemporal theory, and some patterns that are there already in activities of daily living. We have an abductive reasoning engine that runs in answer set programming, and then we select the most interesting heuristics and try to find out what is there in the qualitative world in the video there. So in terms of logical formulation, this is very simple. What I am looking for is this my theory, this is pattern, this is what I am looking for, and this is the video that's coming to me. Okay, so in terms of input outputs, this is all I have. So this is all I have, and I am looking for this output there. Okay, and that is all we have done. So to cover up what that I tried to show you, I went by a very simple idea that abduction may be one way to explain what is happening in the activities of daily living that my AI systems are trying to predict. And that abduction uses affordances as an anchor. So I'm trying to exploit affordance. And for that, I first proved that affordance cues help in reasoning. Then I moved on to show that you can find out semantic affordances automatically and use this in your visual explanation driving to get to the optimized one. So this is all I have for you. If you have questions, I will be very pleased to answer. But basically, this visual explanation is computing what? It is computing in the hypothesis based on abducibles, which are my primitive events and beliefs. And these hypotheses are directly usable for all the motion tracks that I can see, all these activity graphs that I can see, and nothing else more than that. So to finally conclude, these are my final comments. One, yes, abductive reasoning supported by affordance is a powerful framework for explainable AI. A lot of thing has been done. There is a lot of literature there. It's not that I am the one who is looking at it first, but in terms of our novelty, we have looked at it starting from EEG data being collected, used, up to the point when the video is being used. Okay, so we have the whole picture there for people who are using hand exoskeletons. Okay, so what is the future implication? We really need to look at affordance-driven abduction more seriously to advance the ability of AI systems to interact more transparently with humans. That's what my possible thought is. So with that, I would conclude and be ready to take questions if any. Thank you.
Okay, any questions?
Which one?
Slides earlier.
Here,
Just-
right hand side
yeah.
is the videos.
The five.
Yeah, the phi is the videos. The video in terms of the activity graphs. So we convert the videos into the activity graph. So it's the video that I'm trying to explain. And this is my background theory, and this is my pattern, and this is the video.
Videos is described in which language?
The videos will be in low-level numerical descriptions, OpenCV sort of things. But I convert them into space-time objects here using qualitative spatial reasoning, QSR. Very well-found QSR processes are there. So
But now you're doing dynamic thing, no?
Yes, QSR also is dynamic. You can do QSTR. So you create space-time objects here. We call it the space-time tracklets. So the tracklets are what I have here, the space-time tracklets. And here is an high-level abductive theory. So I combine them to get my most optimized consistent hypothesis. So the real stuff is simple computer vision. What is interesting is this stuff that's coming from the abductive theory.
Any other questions for the speaker?
Okay.
If not, let's thank the speaker again.
Thank you very much.
Okay, so our next speaker. Okay, so our next speaker is Professor Amit Kuber, and he's going to talk about a lot of stuff. Euclidean algorithm and the
Just
completeness
Euclidean
theorem.
algorithm is sufficient. Yeah.
Okay, over to you, Amit.
Okay, thanks a lot, and thanks to the CLC committee for inviting me. Well, this talk is mostly about order theory. Yeah? And order theory is something that I feel is an ignored subject in mathematics. We like to compare. Yeah, comparison happens at many levels, but and comparison orders are used as well, but orders for their own sake. Yeah, that is one of the goals of this talk. And while I was working on this paper called Euclidean algorithm for a class of linear orders with two of my students, Shashwat and Isha, then the purpose was not to do any logic. Yeah, in fact, this whole project that came out of our study of representation theory, and while studying certain types of algebras, we needed a particular class of orders, and this was the class that was being used. And we tried to study it independently because it had some applications. And later on, it turned out that whatever we are trying to do is actually a completeness theorem. Okay, so I will show you what's happening. So let's go back to school. Yeah, Euclidean algorithm is something everybody does understand. So we are starting with natural numbers, and to be consistent with logicians, yeah, 0 is a natural number. At least for the sake of this talk, even if you don't agree with it, bear with it. Yeah, the set of natural numbers actually, yeah, anything? Okay. So natural numbers you can think of as the set, you simply start with 0 and 1, and then you add as many times as you want, only finitely many times, and you multiply. So this is the set that you obtain by closing this two element set under addition and multiplication. And similarly, integers is the set which you obtain by closing the same set under addition, multiplication, as well as subtraction. Yeah, so this is something you should probably remember. And what is Euclidean division? If you are given two non-zero numbers, yeah, then there exists some quotient and some remainder. The quotient has this property that its absolute value, the remainder has the property that it's positive. First of all, we assume that, and that its absolute value is strictly less than the value of the divisor. Yeah, just elementary brushing of Euclidean division. And then because there is a decreasing sequence here, eventually some remainder is going to be 0. That is what Euclidean algorithm says. That there is some step after which the remainder will vanish. And we are repeating this process. The notation was set in such a way that it happens. Now, obviously in algebra, like algebraists have generalized this idea, they have talked about Euclidean domains where this algorithm actually makes sense, and then Euclidean domains and the theory around that, like there are special kinds of PIDs. That is an algebraist viewpoint. However, the numbers that we are talking about here, these natural numbers, they themselves are linear orders. So let us look at the Euclidean algorithm in a new light. And think like a logician, so it gives you this talk, yeah. These are finite linear orders, yeah. Natural numbers are finite linear orders. Yeah, in fact, I encourage all of you to ask questions during the talk itself, if you, because my main purpose is to spread awareness about order theory as a subject. And you might be surprised to know that linear orders, yeah, there is only one book available on linear orders, and that was written back in 1980s. So Rosenstein. Yeah, so therefore, yeah, let's recall what this linear order is. So it's, I mean, in a technical term, it's a set together with a binary relation which satisfies two properties, like, a few properties. We can call them asymmetry, then irreflexivity, transitivity, and this special property called as trichotomy, which makes sure that any two distinct elements are comparable with respect to this order. Okay, so I'm going to interchange between less than and less than or equal to, yeah, quite often in this talk. And less than, the omega is the notation. Yeah, actually, like mathematicians have different notations. Omega is the notation reserved for the set of natural numbers with its standard ordering. Whereas when we write just n, usually it refers to the algebraic structure, either with shift operator or with addition and multiplication. And whenever we are talking about one particular natural number, then I'm just going to distinguish it, the number, from the corresponding linear order by writing it bold. Yeah, so now linear orders themselves carry a lot of arithmetic. So for example, if you have one linear order, let us view them as lines, obviously. One linear order and another linear order. Just put it next to each other, that is the sum, order sum. Okay, then we can also do product. And for product, our favorite dictionary dictionary ordering comes into play. And here I am using the anti-lexicographic product, which means the second component is given preference, whereas the first component gets the second preference. So let me be more. No, this is disjoint union. Yeah, so to be more precise, L1 plus L2 has disjoint union. Yes. So basically, we add indices to them. Yeah, the 0th index or first index gets attached to all the elements from L1. Then it is L2, second index, and then we compare. Yeah, so we are not making. We don't need that they are non-overlapping. We should be able to define, for example, omega plus omega. One copy of natural numbers followed by another copy of natural numbers, and this is what we normally do in set theory. Okay, so the anti-lexicographic product, we are taking just the Cartesian product as the underlying set, but the second component is given preference. So whenever we have this relation in the second components, A2 is less than B2, then no matter what happens, that's going to be, the first thing is going to be less than the second one. And if they are equal, then this should happen. Then we compare the first components. And order reversal is another operation. Now think about the previous slide. I said plus, dot, and minus. So order reversal is supposed to play the role of minus sign. Yeah, you say very vaguely. So you simply reverse the order. Instead of less than, we are talking about greater than. Right. But this particular arithmetic doesn't have all nice properties. It is the sum and product are still associative up to isomorphism. Yeah? So that's why many people actually talk about order types rather than linear orders themselves. So order types means order isomorphism classes of linear orders. Yeah, in order types, like making them disjoint is irrelevant. It automatically works. So associativity of sum of order types, associativity of product of order types, but these operations, they differ from usual arithmetic in the main aspect that these are not commutative. Yeah, you take linear order 1 and then you put a copy of omega after that, you get 1 plus omega, but 1 plus omega is just omega. Order theoretically it is not changing, whereas doing omega first and then adding a 1, then there is a gap. Yeah, there is an infinite jump to go from any element of omega to go to this last element. So that's why it's not commutative. And similarly, multiplication is also not commutative. And distributivity is another feature that we often encode in the definition of rings, that multiplication distributes over addition from both sides, but here it only happens from one side. So left distributivity, but not the right one. I mean, essentially, let us revisit product again. What we are doing is we have L2, yeah, a linear order L2, and we replace each element of linear order L2 by a copy of L1. That is what this product is. Yeah, it is also an ordered sum indexed by L2, where each element is actually, where each summand is L1 itself. Yeah, any questions about this so far? This is left distributivity. I mean, let's do an example here, that 1 plus 1 is 2. And 2 dot omega means that you are taking omega and then replacing each copy with 2 elements, 2 element linear order. Well, you are not going to get anything different. It's just omega. Whereas omega dot 2 is omega plus omega. There is a gap in between. Okay, so therefore order theoretically they are different, and that's why 1 plus 1 dot omega is not same as 1 dot omega plus 1 dot omega. Yeah, so only left distributivity holds. The indices that we have, we can add them and you can separate those things out, but not otherwise. Okay, so finitely presented linear orders, this we coined this term. It is the smallest class of linear orders which contains 0, 1, and yeah, I think I forgot to mention omega, and that is closed under order isomorphisms, sum, product, and reversal. Yeah, same thing as integers. Yeah, this is no. I mean, right now, no. Yeah, there is some other work about rationals as well. So you can close it under order isomorphism is must. Yeah, we are just changing the names of elements. So isomorphisms is obviously we have to take care of that. Sum, product, and reversal, plus, dot, and let's say minus or star. Yeah. Then we'll recover ordinals up to a certain point. Can you guess which one with this? No, it's omega to the omega. Yeah, omega to the omega. Yeah, so that's how actually ordinals are also built. Yeah, and then I think epsilon naught is where the arithmetic starts failing. Yeah, you cannot go beyond that. So yes, so reversal is the key feature here. Yes, for all order types, arithmetic. Yeah, we are actually lifting the arithmetic from ordinals to all order types. Okay. Now, yeah. So because I forgot omega, yeah. A linear order is finitely presented. I mean, usually finitely presented simply means that you start with some basic symbols and in finitely many steps you can generate it. And that is precisely happening. So we are saying that if and only if it can be constructed from 0, 1 and using these 3 finitary operations. The first operation is a binary operation. Yeah, this is not a minus sign. Yeah, this is just a placeholder, binary plus, then something dot omega and something dot omega star. Now this is actually quite surprising, yeah, at first, that we just have to take products with omega and omega star and that is sufficient. But thanks to left distributivity, this can happen, yes. Omega star is the reverse, yes. Yeah, like negative integers, yeah, the order type of negative integers, correct. So using left distributivity as well as associativity, this can be done. Yeah, you just have to be able to multiply by omega and multiply by omega stars. So this actually introduces the language. Yeah, this particular statement introduces the language. And there are some standard isomorphisms as well. Now, as I mentioned, 1 plus omega is omega. So I can pull out maybe 5 elements from the beginning and it is still omega. What remains is still omega, and that is precisely what is captured by this first property, which we call exude, that you can take L1 plus L2 dot omega and leave out, like pull out one copy of L1. What remains inside is L2 plus L1, L2 plus L1. And you can do that without changing the order type. So you can, similarly you can do exude star, which is on the other side. You can pull out one copy of L2 and just the pairing changes. And moreover, this is just associativity, but I have written it explicitly for a specific reason, and I will show it on the next slide, that L1 dot n dot omega plus minus means either omega or omega star. You can use associativity and you will get L1 dot n dot omega plus minus, but n dot omega plus minus is again omega plus minus. So that's why this can happen. However, the key takeaway from this particular slide is this theorem, that you can build everything only using these 3 steps.
Can you please explain the second one a bit?
The exude star. Yeah, so for example, I mean, do I have a chalk here? No. Yeah. It's here. Thank you. So basically, you have L1 plus L2, yeah? So L1 plus L2 just looks like this, yeah? And dot omega star is actually this. We are doing this. And now we are just bracketing it differently. We are saying that I can do this instead. Yeah. I can pull out L2 and then the remaining things are here. Yeah, bracketing from the right side. It's just actually a change in bracketing, nothing else. Yeah, these are like everybody is happy to accept these properties. Yeah, these are naturally true. But the interesting thing is that these are sufficient to conclude any isomorphism. That is the main point. Okay. So let us try to use this theorem that everything can be generated using plus minus and plus then dot omega and dot omega star. We will try to write it in terms of trees. Yeah. In fact, 3 sign trees. The 3 signs correspond to what I just said, the 3 operations. Okay. This is not our idea. This is the idea of Montalban. He used it for dot omega and dot omega star, but they were only sign trees, 2 sign trees. We also needed to add some rigidity, and that's why 3 sign trees. Okay, so rooted tree, the technical definition is complicated. It simply says, I mean, if you understand trees, between any 2 points, it's a connected graph such that between any 2 points there is a unique path. Now here we are talking about a root. So which means starting from the root there will be branches which will never interact with each other again, unlike banyan tree. Yeah, so the mathematical way of writing it is a well-founded subset of finite subsets of omega. So normally what we do is something like this, like we have empty, then we have, and the technical condition written there that if I know that there is a child of the empty set which consists of 1, then there must be a child with label 0. That is the technical condition. So if I know, for example, I have 1, 2, then I know that there is 1, 1 and there is 1, 0 before that. Yeah, written to the left of that. And well-foundedness means that if I know that, let's say 1, 0, 0 is there, then I know that by hiding this part, 1, 0 is also there, and by hiding this part, 1 is also there and empty is also there. So well-foundedness just refers to this, that if you eliminate some or all last symbols, then that node is also again in your tree. So this is a rooted tree. Okay. Now finitely branching, yes, because it's omega to the less than omega, so it's a finite subset. Yeah, that is more important. Yeah. Then a 3 sign tree is this tree with a function, and it simply takes 3 values, 0, plus or minus, and these 3 values, like the 0 value is specific, it is taken only at the root or at the leaves and nowhere else. Plus and minus are the only signs taken at other points. Okay, and I will give you an example very soon, which is this. So in the parenthesis I have shown the signs. Yeah, so empty set, then 0, 0, 0, plus is the sign here, plus is the sign here, and well, what are we doing with this? We can associate a linear order to every 3 sign tree in a natural way. So you start reading it from the left, the ordering of the vertices actually plays an important role. So this is 1. Yeah, whenever it is not root, it's a leaf, then that represents the linear order 1. So 1, 1, 1 everywhere. Okay, now we are just going forward for some reason. Okay, so this is just 1. Then plus at the top means, plus as its parent means that you have to take omega, product with omega. So this branch is omega. This branch is omega star dot omega. And this branch is, omega star plus 1 dot omega. And the last branch is just 1. So that is what I have written, and I accidentally touched it again, so maybe I should keep this here. Right. So this is a presentation for omega plus omega star plus 1 dot omega plus 1. And the same thing is actually true here. This is also a 3-sign tree presenting the same linear order. Yeah, I'm not going to go into too many details, but just notice that here we had this longer branch first. We exuded that particular branch outside. The first one we took it outside because this is a plus sign node, and then the order of the children were cyclically permuted. Something very simple. So that's why those 3 operations were important. Yeah, exude, exude star, and n replicate. I haven't given you an example, and this is the more technical definition of how to assign a linear order. It's an inductive definition, and as you can easily see that every tree has a height, how deep do we go, and every tree also has a width, and width is simply the number of children of the root. Now, if there are 2 3ST presentations, then one thing is good, that for the same linear order, then the height won't change. The height is going to remain constant, but their form can change. Yeah, the trees themselves can change a lot. Their height won't change, however. Okay, so if we want to do something like Euclidean division or Euclidean algorithm, then we should have some parameter that helps us cut down the number of steps. Yeah, something which eventually will stop. Something has to stop after some time. So the rank is defined to be the height of the rank of the linear order is defined to be height minus 1. And this actually coincides with the definition of Hausdorff rank, which obviously Hausdorff introduced. Yeah, that's why we call it Hausdorff rank. And I will not go into that technical detail. And because of this theorem, no matter which presentation you choose, the rank is well defined. But the width, yeah, this is the new parameter, that width is the minimum number of children in a tree presentation for that linear order. Minimum number of children. We know that there is a tree presentation, 3ST presentation, so therefore, and natural numbers are bounded below. So that's why the minimum number does exist. Okay. So this is the width of a linear order. Yeah, we are not here, here we are not talking about a tree, but a linear order. And this is the Euclidean division that I promised in the title. So suppose there are 2 linear orders. Now first try to just imagine that L and L dash are 2 natural numbers, n and m. They do satisfy this particular hypothesis that n dot omega and m dot omega are isomorphic. Okay, so because they satisfy that and such that L is a prefix of L dash under this isomorphism. Let's assume that. Prefix means something which is in the beginning, suffix is something which is in the end. Yeah, so it's a prefix of L dash under this isomorphism. Then there exists a quotient. Now quotient is still a natural number. There is a quotient and a remainder. Okay, so that is what we are talking about, and a partition, actually partition of L such that L is equal to L1 plus L2 such that this happens. So L dash is L dot K, yeah, means L1 dot L1 plus L2 dot K plus L1. So L1 is the remainder, and L1 plus L2 dot omega is isomorphic to L2 plus L1 dot omega. So not much is changing in terms of, I mean, the same hypothesis can be repeated. We just have to ensure that afterwards. Now there are two possibilities. Now this is obviously a linear order generalization of the Euclidean division. So we have to ensure that something goes down. So either rank of L1 is smaller than rank of L2, in which case L1 dot omega, like not just L1, but in fact L1 dot omega itself is a prefix of L2, or the dual, or the last case is the interesting one here, that if their ranks happen to be the same, then the width, the minimum of the width actually goes down, and therefore eventually your algorithm will terminate. Without this last condition, you can't achieve that. Okay. Yeah. Huh? K is unique. Yes, K will be unique. Yes, but like if you are fixing this isomorphism, then K is unique. Yeah. Okay. So let us say that these three sign trees are equivalent if there is a sequence of standard procedures. The standard procedures, maybe I should remind you, exude, plus minus, and replicate. If there is a sequence of them or their inverses which converts one 3ST into another 3ST. Now, because each of those steps does not change the order type of the linear order, we have the soundness theorem. Yeah, every step preserves the linear order up to isomorphism, so therefore finitely many steps will preserve. But the more surprising thing, which can be proved due to Euclidean division or Euclidean algorithm, is that if there are two 3STs whose corresponding linear orders are isomorphic, then actually they are L equivalent, which means there is a finite sequence of these basic steps which you can figure out between them. Yeah. So this is the completeness theorem. Of course, now it doesn't look like a completeness theorem. It's the isomorphism problem for this particular class of linear orders, and we are thinking of these exude, plus minus, and replicate as our valid rules of proof. And we are saying that every isomorphism has a finite proof. Okay, so let us look at some history of its logic connections. So Cantor was the first person, yeah, who introduced, we can say set theory, but he also did this categoricity of the theory of dense linear orders. Yeah, you asked me a question about rationals. So rationals are going to enter the picture now. So rational numbers, they are the only dense, unbounded, countable linear orders up to isomorphism. And the technique used to prove that is called the back and forth method, and standard thing taught in a model theory course. So Skolem and Tarski afterwards, they introduced shuffles. Yeah, if I may talk about shuffles for a bit, I think I have some time. So eta is the notation that order theorists use for rational numbers, yeah, just to emphasize on its order. And suppose we are given red, blue, and green as three colors. So we want to color rational numbers using three colors such that between any two rational numbers, there is a point which has red color, there is a point which has green color, and there is a point which has blue color. So every color should occur in a dense fashion. Okay, so we are asking for a coloring function, I am just going to call it chi, a coloring function which is dense, which means we are every linear order, and then we can ask whether there exists one, first of all, such a coloring, and there does exist one. You just have to use some basic number theory, yeah, that maybe all the rational numbers which have some specific type of denominator, yeah, all powers of a certain fixed prime, then those are all red. Then powers of another fixed prime, those are blue, and the rest of them, those are green. So these are all dense subsets of rational numbers. So there does exist one dense coloring of rational numbers with 3 colors, or in fact with any number of colors, and in fact also countably infinitely many colors. Okay? And moreover, the same back and forth argument can be shown, can be used to show that this coloring is also unique up to isomorphism. A dense coloring is unique up to isomorphism, which means all the points, there is an isomorphism between two copies of rational numbers such that all the points which are getting red color in the first one, they will get mapped to the points which are getting color 1 in another linear order. Okay, so that is a very strong technique for countable structures. So this is Kolem and Tarski actually, but I mean, this is attributed to them, but we can't really find it in literature. Yeah, their students or their descendants have just written about these things. Now, okay, so how are we going to use this RBG to define some new linear order? Yeah, the interesting part is that if I have 3 linear orders, LB, LR, LB and LG, corresponding to each color, I have one linear order. And then what I do is I take summation of L sub chi little r, where r is varying over rational numbers. So I take an ordered sum of rational many copies of these things. So I have rational numbers in a linearly ordered fashion. Then at every rational number I check, is the color red? If yes, then I replace that with LR. If the color is blue, I replace it with LB. And whatever I get, now obviously you might think that this particular ordered sum depends on the choice of coloring. But the coloring itself is unique up to isomorphism, and therefore the order that you obtain is also unique up to isomorphism. This is the so-called shuffle. Yeah, so Skolem and Tarski, they introduced shuffles, and in logic, like the direct connection came from Leokley and Leonard's paper back in 1968. Who studied the order types of orders in LOFP as well as LOFD with EF games, Ehrenfeld-Freise games. So this is some graded versions of elementary equivalence and elementary equivalence. I'm not going to go into how to play those games. Yeah. Yes. FD is finite description linear orders. I was going to say that. And LOFD is you close 0, 1, omega under addition, multiplication, reversal, order isomorphism, and shuffle. So if you close it under shuffle, then also you can play the same game. Now for, to be a bit more technical, if you have so-called scattered linear orders, in which, like the orders in which rational numbers cannot be embedded, the scattered linear orders, they are for any given n and a given scattered linear order, there will exist one LOFP, a finitely presented linear order, which is n equivalent to that scattered linear order. Whereas if you want to play the same game with any linear order, then you need LOFD, finite description linear order. It's a finitary operation on linear orders. Normally we don't have many finitary operations, naturally occurring finitary operations. So for every n, the shuffle gives you a way of constructing a finitary operation, n-ary operation on linear orders, which is uniquely defined. Yes, yeah, I mean shuffle, I should have brought in a deck of cards and then talked about it, that yeah, so if you shuffle, perfect shuffle is like any card can appear anywhere. Yeah, and that is precisely the idea, via the name as well, shuffle. Okay, so this was the direct logic connection. But later on, it seems that computer scientists picked it up, and Heilbrunner and Korsel in 70s, in a series of papers, they studied connections with word problems and context-free grammars. I was not aware of this connection until this year, okay, 2024, because the language used in linear order theory and word problems and context-free grammar is entirely different. Even a Google search cannot give you anything useful. Yeah, that you are trying to search for Euclidean algorithm or LOFP. This LOFP was actually studied by Lockley and Leonard, and they just called it M0. Now, there is no way that by a Google search I can find out that M0 is LOFP and M is LOFD. Yeah, we needed both of these things in representation theory, but yeah. So based on this work of Heilbrunner and Kursel, eventually, I mean, these people, they published several papers. The first one of them, Bloom and Essex paper, is word theoretic proof of the completeness. And you simply replace the order types with words. Then the operations are concatenation, actually, plus is concatenation of words. These are all countable words. Then they can, dot omega is replaced by a word to the power omega. You repeat that word omega many times on the left or on the right, and they studied it using this. They call it regular words, and encodes associativity of plus, exude, and replicate properties for n bigger equal to. These are their axioms, and they actually call it a completeness theorem. We never called it the completeness theorem, but they did. And we only recently figured that out. And the same thing for LOFD. That has also been done. And we were completely aware, and we came in much later. And the main takeaway is that, yeah, whatever result you are trying to prove, maybe it is already proven. You just don't know because it was a completely different language. Okay, and I'll stop here. So these are the references. So thank you. Yeah.
Questions?
Huh?
Iterations, like you said that Eshik and they were doing, repetition of the thing. So if I just look at finite iteration, but unbounded.
Finite iterations?
Yeah, I mean finite repetition, but unbounded.
Okay.
Will I get something new from these, or because?
I'm not sure.
Okay. Yeah.
I haven't
Just
thought
curious.
about it.
Because, Eshik and Co, it's probably they have some version of finite iteration, that's why I asked.
Okay.
They may have. So
I haven't checked their other papers so far.
Okay.
Do you have any explanation why there is just one book on linear order?
People generally don't pay attention to that. Yeah, people think that, yeah, orders, yeah, fine, they are there. Yeah, you don't actually want to study orders for its own sake. This is also interesting, like combinatorics people or set theories, they pick up these problems. Yeah, but order theory as a subject on its own, that I don't think has been done. Usually it branches out into something else. You start studying prosets, then from algebraic perspective, then it becomes algebra. Then lattices, it becomes lattice theory. Yeah, you need more structure, but linear orders themselves have beautiful structure, and I don't see many people actually actively working on it.
Do you see, can you guess any remote connection with Conway's approach to numbers?
Conway's approach to numbers?
Numbers.
Yeah, there should be.
Do you think?
You mean serial numbers?
Yeah.
Yeah, serial numbers. Yeah, there should be, because we are again, but like just because of involvement of trees, yeah, trees will appear in trees or graphs, they always appear in any discrete structures. So I can't really say for sure that this is the reason why we are doing it.
Any other questions? Okay, if not, then let's thank the speaker again. So we will now break for lunch and come back at 2:30.
See,